Alright, today's video we're going to go over how to determine if a molecule is polar and then also be able to draw their dipoles. And so let's go through a really simple example of this with HCl as our first example. And so HCl, our first thing is always to kind of just draw this bond or whatever bonds we have in this molecule. In this case, we have an H and Cl. I guess you could also draw the lone pairs, and that's be how you start off with. Then, I guess our real first step is to determine if this is a polar bond or not, and that is by finding the difference in electronegativity. And if the difference in electronegativity is between 0.5 and 2.0, then it is polar. And so what we have to do is find the electronegativity or the electronegativity of H and Cl based off of the Pauling scale. And so if we look at these values, H is over here at 2.20 and Cl is 3.16. And so we have to use those two values to calculate the difference. And so Cl, once again, is 3.16. H was equal to 2.20. And the difference between these two values is 3.16 minus 2.20 is equal to 0.96. And so obviously, since this is in between our two values that we had before, this is a polar bond. So HCl, this is a polar bond. Now our job is to draw the dipole based off of where these things are. So the higher dipoles will always look like an arrow, where this is your negative side or your partial negative side, and this is your partial positive side, right? And the higher the electronegativity value, the more likely it'll be negative. It's just usually the negative value. And so in this case, since Cl has a higher electronegativity value in comparison to H, we know that the Cl in this molecule will most likely be the negative one. And so this is where we draw our dipole, where the H, our second atom, will be the positive, and it'll be pointing towards Cl because we know that Cl will be the negative side because it has a higher electronegativity value. And so this is the dipole of the bond. And if you wanted to draw their partial charges, you'd do a partial negative and a partial positive. In this case, since we only have one bond, right, that is the total molecule dipole, and so we don't actually have to draw anything more than that. So let's go through another example of this with CH2O. And so the first thing is always obviously have to draw this. And so we have to know how to draw this based off of molecular geometry. And so if we knew the molecular geometry of this, we could draw it as such, where this is a trigonal planar molecule that looks like this. And so based off of this, our first step, once again, is to find the electronegativity difference between these two values. And so now we have different types of bonds. We have, for step one, we have to look at our C-double-O bond. We also have to look at our CH bond, because those are the two types of bonds that exist in this molecule. So our first step is to find the difference between electronegativity of C and O, and C and H, and determine are they polar or nonpolar. So let's look at our values. C is 2.55 and O is 3.44. And so this is 2.55. This is 3.44. And then from before, we already know that H is 2.20. And so this is 2.55. And this is equal to 2.20. And so let's figure out the differences in these electronegativities. So 3.44 minus 2.55, and then this is going to be 2.55 minus 2.20. And let me pull out a calculator real fast to calculate these things. So 3.44 minus 2.55. Sorry, that's taking a while. This is equal to 0.89. And then this is equal to 0.35. So in this case, this bond, CO bond, this is a polar bond since it's in between 0.5 and 2.0. While our CH bond is nonpolar since it's less than our values here. And so if it's less than those values, this is a nonpolar bond. So if it's 0.5 or below, it's nonpolar. And so in this case, we know that this bond right here is nonpolar. We know that this bond right here is nonpolar. And so we do not have to draw any dipoles. And so there are no dipoles in our molecule in terms of those. However, our C double O bond with O has a dipole. And once again, the higher of the two values is where the arrow is pointing to. And so in this case, since oxygen has a higher electronegativity value, we know that this will be pointing towards our oxygen up here. Once again, if you wanted to draw these as partial positive and partial negative, we know that the partial negative will be on the oxygen, the partial positive will be on carbon. And that is, once again, since there's only one dipole in this molecule, that is the entire total molecular dipole as well, since there's nothing else in this molecule. So let's go through a third example of this, where we have to start thinking about molecular geometry, but also have to look at how these things interact with each other in terms of when you have multiple dipoles. And so let's look at an example of H2O. And so our first step is to always draw this, right? So O, H, H. It has two lone pairs on the top. And this is a bent shape, right? And so we have to know, once again, the molecular geometry. Our first step, once again, is to always find the difference in electronegativity. Remember, it has to be between 0.5 and 2.0 in order for it to be polar. If it's less than those two values, so if it's below 0.5, then it's nonpolar. And so we have to figure out the difference between our values of O and H. And so let's look at our chart. Oxygen is 3.44. Hydrogen is 2.20. So 3.44, 2.20. And so we calculate the difference between those two, 3.44 minus 2.20. And that is equal to 1.24. And so we know that this is going to be a polar bond. And so every single OH bond we have in this molecule is going to be a polar bond. And then once again, since oxygen is the higher electronegativity value, our arrow is going to be pointing to this. And so this bond will have an arrow pointing towards the oxygen, and this one will also have an arrow pointing to the oxygen. And so now we have two dipoles that we have to factor into this molecule to draw its overall molecular dipole. And so when you have two dipoles, you have to be able to add them together. There's two kind of methods you could think of this. The easiest way to do this is by thinking about the midpoint of these two vectors and kind of adding those two things together. And so if you think about this, our starting point, if you think about our starting point of our vector here, and we think of our other starting point here, and they're both pointing towards the center area, the midpoint of these two starting points would be here, right? And then our endpoint is that both of these arrows are going and pointing towards the upwards direction. And so if you added those two vectors together, it would also be just pointing upwards. Although in this case, it would technically be higher than those two. But in this case, we could just make it simple and make it that they end up in the same area. Then all you do is that starting point that you had is now your plus area. And so we could redraw this as your total molecular geometry. Sorry, this is a little messy. I'll erase those. And so your total molecular geometry will look like the following. So O, H, H. Bonds here. Your dipole is pointing upwards through the oxygen. I guess you could also draw this through it. So let's kind of draw that as well. I'll change the colors so it's a little bit easier to see. So it'll look like this as your dipole. And remember, this is your negative charge, and your positive charge will be over here. So technically, both of your hydrogens have partial positive charges. If I went back to the same colors I had earlier, or similar colors to earlier, this is your partial positive, In this case over here, sorry, these colors are going to be slightly different now, which I know is going to be a little annoying and obnoxious, but this will also be a partial positive here. And your overall partial positive is going to be between your two hydrogens, and your overall partial negative will be at your oxygen. And so that is how you draw your total molecular dipoles, is by doing those two things.